Hello, my name's Peter Horter. I'm going to be running through a series of videos to introduce the particle physics topic from AQA using my PowerPoint resources that I would use in class. Particle physics is the study of the atom and the subatomic particles. So you'll have come across the protons, neutrons and electrons, but it turns out the protons and neutrons are made up of smaller particles still, and there are particles associated with the electrons that are of interest to physicists. I'm going to depart from the route that most textbooks take. They tend to look in a chronological order at the developments of the subject from the late 1800s onwards and the discovery of the different particles. I'm going to approach this by giving you the final solution of what our current thinking is, and then look back at the history of that development in light of the final answer that physicists currently have. I think this gives the advantage of seeing the simplicity and seeing where we're heading. Many scientists were confused by the results at the time, and therefore we end up with particles with unfortunate names. And the process of discovery makes perhaps the process of understanding difficult. Seeing the simplicity and symmetry of the final theory allows us to look and maybe make more sense of some of the aims of the course. So pause the video here and just ensure that you've got all the stuff ready to both follow along with the questions, but also to take some notes. The reason I'm videoing these courses is the names and the ideas can be quite difficult, and so an ability to look back, to pause, to try things at your own pace, so that in class we can do questions and then find out where people aren't sure and focus on the key difficulties rather than the general material. Right, if you've paused the video and you're back with us, then this is the content given in the AQA specification for the first area of particle physics, and what I'll basically be looking at today with a few small additions. So right back from even pre-GCSE, you've thought of the atom as a solar system style model, sometimes called the Rutherford atom, after Lord Rutherford, whose PhD students effectively came up with it. So it's got a very dense central core called the nucleus, which contains the protons and neutrons, and then the electrons orbit a bit like planets. Just like the solar system, almost all of the mass is concentrated in the center, and just like the solar system, the center is tiny compared to the whole. So if you take the school hall, then you're probably looking at something smaller than a pea at the center of the school hall, representing the relative nucleus to atom size. The diagram's not perfect. It shows all the electrons orbiting at the same distance, and you'll know from GCSE that they orbit in shells. So taking that first point, which is entirely GCSE revision, we've talked about our simple model of the atom. The protons and neutrons in the center. If there are, say, 6 protons and 6 neutrons, we would say the nucleus has got a relative mass of 12, or a mass number of 12, and at A level we call that a nucleon number. Protons and neutrons are both nucleons. And then if it's got 6 protons, it would have 6 electrons orbiting. Atoms are neutral. So we need to know the mass and the charge of the items in relative units. That's what you've done at GCSE. So +1 for the mass of the proton, +1 for its charge, and so on. And we won't be revising those. But it also says in SI units. Now, we may not have covered SI units by the time we start this course, if it's the first one that we're given. So all we mean at this stage by that is things like kilograms, coulombs, meters, seconds, that sort of thing. And this information is to be found on your formula sheet, so you should hopefully have it. If you look on the front page, you would be able to find the data for the mass of a proton. About 2/3 of the way down that front page list is 1.67 times 10 to the minus 27. It's a small mass. So that's why we use this relative mass to help us. The relative tells us protons and neutrons are, to all intents and purposes, the same mass, certainly to one significant figure. And you'll be able to find, say, the mass of the electron, and much nearer the top, you would find the charge of the electron. Now, that's the only charge given, because you know that if the charge on the electron is 1.6 times 10 to the minus 19, the charge on the proton is the same magnitude, just the opposite sign. And the neutron is 0. That doesn't need any information. Okay. So a reminder from GCSE again. The top number on the left, superscript, we'll call it the nucleon number, but at GCSE chemistry you would have called it the mass number. It's simply the number of protons and neutrons. Remembering that they have a mass of 1 each, in relative terms that's why. And the atomic number we'll call the proton number, Z, and that's just the number of protons. That defines the atom or the element. Now we'll come to talk about relative charge a little bit later, but that's when we talk about ionization. Now here I've got 3 different examples of atoms, and you can see they've all got 6 protons, and everything that's got 6 protons in its nucleus is carbon, and all carbons have 6 protons in their nucleus. But what we can see here is this carbon 12 has 6 neutrons, so we've got 6 plus 6 equals 12. Carbon 13 has 7, and carbon 14 has 8 neutrons. Okay. These are isotopes of carbon. As I've discussed, if you want to calculate the number of neutrons, you would do 14 minus 6. And just a reminder that when we're reading this, we'd read the middle one, however it was written, we'd read it as carbon 13. And sometimes people omit in the standard notation the 6 at the bottom, because you can go to any periodic table and find out that all carbons are 6, but not all carbons are 13. So that's the additional information. Right. A reminder about ions. An ion, as it says there, is an atom that's lost or gained electrons. It's no longer neutral. And ionization is just the process of making an ion. 13.6 plus, we omit the number 1 there, but if it was 2 plus, clearly we can't omit the number 2. That's a carbon ion. It's lost a single electron. Remember, the number of protons can't be affected. All we can lose is electrons from the outer shell. It's lost a single electron, so its charge is, well, it's got now 6 protons and only 5 electrons. So it's got a charge of plus 1.6 times 10 to the minus 19 coulombs. But you might probably, hopefully, find it quicker to just see that, well, it was neutral and it's lost a single electron. So all of its protons are cancelled out bar 1, so it's got the charge of that 1 proton. Right, we need to be frank at this point. It's probably early in the AS course or the Year 12 course. Time is short on this course. Everything I've discussed so far is GCSE material, and we don't have time to go back over it. We don't even have time to think deeply about it as we run through this course. That knowledge will just be assumed. And if you're working hard to try and work out the charge on an ion, or what is an electron the same magnitude charge as a neutron or a proton, if you're having to think about those things in class, you're going to miss the new material. So whether it be flashcards, whether it be somebody testing you at breakfast every morning, you've got to do something to get that knowledge totally assimilated so that it's just comfortable for you, so that the new material can build on top. Otherwise, we're building on shaky. Right, so here's the first new material for the course, specific charge. Okay, this is historically a really important measurement for charged species. Clearly a neutron doesn't have charge, so its specific charge, as you'll see in a moment, will be 0. But items that do have specific charge, comparing their values is really important. Now the formula sheet is very comprehensive, but specific charge is not on there. Okay, so it's a surprisingly simple formula, just a 3-item, like speed equals distance over time. It's done very badly at A level. People assume it's easy, they don't revise it properly, and then the examiner's reports regularly say we were surprised that again this year a certain proportion of candidates could not work out the specific charge of simple species. It's quite like density if you want to think about it, so you sort of have a feel for it. If something's very dense, it tells you the mass is squashed into a small volume. Okay. Specific charge tells you how concentrated the charge is in comparison to not volume but mass. Okay. So if something's strongly charged and light, low mass, an electric field will deflect it a large amount. And that's what we're talking about when we think about specific charge. It's very simple. Specific charge is charge over mass, which means its units are the units of charge, the coulomb, divided by the units of mass, the kilogram. So some examples for you, taken straight from the formula sheet. So the proton charge divided by the proton mass gives us a figure of roughly 10 to the 8. Okay, roughly 100 million coulombs per kilogram. The neutron is, as we said, 0, and the electron, well, the top number is the same as the proton, but the bottom number is much smaller, and we make the bottom number, the denominator, much smaller. That makes the overall answer much bigger, and this is 2 times 10 to the 11, much larger number than the proton. And when this was discovered, when we measured the charge to mass ratio, or the specific charge of the electron, people were incredulous. They could not believe it was so much bigger. And at that point, they didn't know, well, is it something with a much larger charge or a much smaller mass? And obviously, we've subsequently discovered that. Just some notes, NB, take note if you like. People often talk about magnitude. So we'll often compare the proton and the electron. When we're comparing them, we're implicitly comparing the magnitude, and we assume knowledge of that negative sign. But in an exam, you should put that there. In this context, I quite often see examples of students forgetting that these two items have the same charge, even though they can tell me that when asked directly. Hidden in a question, people maybe forget. And as I've mentioned, the electron has a much higher specific charge, roughly 2,000 times bigger, because its mass is roughly 2,000 times smaller. Right, so how will you be examined on this? Well, it will be part of a question or a multiple choice question. As we move through the course, we might find some shortcuts to answer multiple choice questions, but here we'll just look at the basic method of how to work it out. So you'll either be asked to work out the specific charge of a nucleus, so therefore you're just talking about the positive charge on the protons and you can ignore electrons because the nucleus doesn't have any, or you'll be asked about an ion. So then you've got to make that mental distinction. You need to think about how many protons are in the nucleus, how many electrons remain on the shells, and that might be fewer than the number of protons for a positive ion, or greater than the number of protons for a negative ion. So our worked example, calculate the specific charge of a carbon-13 nucleus. So its charge is 6 protons. Because from the formula sheet, we know the charge of the electron. Its mass, well, it's got 13 protons and neutrons. So we can work out 13 times this. Now you'll notice on the formula sheet, there's an extra digit, a 4th digit in brackets. We can ignore that for all but one topic in year 13. We can treat protons and neutrons as the same mass all the way through year 12. So that 3 in brackets there, we don't need to worry about. So the charge over the mass, hopefully you had a go before I put it up. And it's roughly half that of a proton, and maybe pause and have a think about why that's half the value. The proton was 9.6, I think, times 10 to the 7. If you're just coming back to me, then that value is half, because effectively we've got roughly half of our nucleus is protons, but the other half has mass but no charge. So we've made the bottom bigger, but not increased the top by the same proportion. So the other option is calculate the specific charge of a carbon-13 2- ion. Right, so now we've got to involve the electrons. Right? We don't have a charge of 6 because of the protons. We used to have neutral, and we've added 2 electrons. So we've got a charge of 2 lots of the electron charge. And as I say, lots of students get this wrong. Right, next, we've got 13 nucleons plus 8 electrons. Now, they don't weigh very much, but the examiners want to see that you understand that they're there. So they really barely affect this number, only in the sort of maybe the third or the fourth significant figure. It's much smaller, and you might like to pause and think about why. Clearly, it's because we've made the top number, the charge, much smaller. We've added 8 electrons, so 6 of them cancelled out the protons and would have given it a 0 specific charge, and we've only gone 2 more. Right. This is a slide to have a think about. Okay. It's just touching on what I mentioned about, does the answer change that much with the electrons? The point is that the examiners want to see you understand what's there. Right? You're working out the specific charge of something. You should make sure you show them you understand what's there. This is something to read through, have a think about. It's not something to worry greatly about, but as we go through the course, we'll introduce the idea of using proportionality. Has this number stayed the same and this number got twice as big? What does that do to the answer? So this is something to pause and think on, and maybe ask me some questions in class, or come and see me in one of the sessions. So some questions. Here's one to start you off, and then I'll be setting some on Teams from Caboodle, but at the moment I don't have access. Thank you.